Today, I'll be talking about adversarial fairness in the labor market. I hope everyone can hear me. Not getting any feedback from the backstage comments, so I might check in a couple minutes to make sure that there's that the slides are going through and everything's and the audio is working. My name is Patrick Hagerty, Chief Data Scientist at Arena, and I'll talk about adversarial fairness in the labor market. So just a little bit of background on me. I've been in machine learning for over a decade. I spent over 10 years at the U.S. government doing doing applied mathematics in different fields. In the last 5 years that I was there, I was really focused on machine learning aspects. And after that, I went to In-Q-Tel and worked a lot with the labs there, and worked particularly on enhancing satellite imagery using some of the emerging neural network structures. And I arrived at Arena Analytics, and I'm applying some of the same type of generative adversarial networks to the labor market. So love to tell you today about some of the really interesting impacts that we're having with such new tools. So the detailed abstract summary is that we're going to use adversarial networks to battle or to combat unconscious bias and sometimes conscious bias in the hiring process. It's a little bit different than the generative adversarial networks because there's not only a decision whether it's real or not, there's actually another cost function that we try to optimize. So that's a little bit of a different strategy, but we'll talk about not only some of the details of what we do, but we'll also talk about some of the ways we communicate the power to the clients. And here the clients are not necessarily machine learning experts. The real impact of this that I think differentiates it from a lot of the other machine learning aspects that I've had is that this is a scaled production environment. There's lots of things that I've done in the lab or an experiment or to prove as a proof of concept, but to deploy this as a production level machine learning effort was added another layer of complexity, and we'll talk a little bit about that. So the first thing I want to stress is that there's inefficiency in the labor market. This might not come as a surprise, but the hiring process, if you're looking for a job or trying to hire someone for a job, it can be frustrating. And a lot of our employers realize that they're bad at hiring. There's lots of reasons why that's a difficult process. Sometimes there's too few applicants. Sometimes the order in which you see applicants is not the ideal order. And sometimes you just have a fixed amount of time, and you might have only time to go through 10 good resumes in a row. And after that, you don't even look at what's at the bottom of the pile. And sometimes you just look at what's on the top of the pile. So last in, first out type of phenomena. So there's other things that also make the labor market inefficient, especially at some of the entry-level positions. There's often qualifications that are required that aren't directly related to performance. I think everyone's has seen the number of years of experience required for a certain job role. And what we want to do is we want to identify which of these requirements really are correlated to success in a position, and which are sort of maybe irrelevant requirements that might prohibit you from hiring a really good person. Certainly the unconscious and conscious bias is the heart of this talk, and how to address that, how to use machine learning to tackle one of the most one of the problems in the hiring process that could have a large impact on some of the oppressed people or oppressed parts of our society. So I think it's great that we can use these tools such as generative adversarial networks to actually make an impact in a positive direction when it comes to labor. And one of the things that we learned from a lot of employers is that they fail to analyze historical data, whether it's why someone was terminated, why someone was hired or what made someone a good or a poor hire. And one of the sort of misconceptions that we have to explain to our clients that there's really no such thing as a good applicant. An applicant is one part of a multi-sided problem. There's the applicant, there's the job, there's the employer, maybe which specific department that they're employed. All those combined in order to have a successful tenure, a successful experience in a job role. So you might have an applicant that thrives in one position or one client, but does not thrive at another client. And we want to sort of disabuse the employer, saying that you have to maybe stop looking for what's sort of called good applicants, but try to find good fits. And that's where we use some of our machine learning techniques. So the typical strategy is that we have a bunch of data, we have a target metric, and we apply the standard machine learning templates. But I'd like to go into a little more detail of what makes this problem probably a little bit different than other problems. Data collection. Data collection is much more difficult in this setting. We get data from the applicant. We get data about the jobs. Lots of third-party and open source data about the region where the job is and the actual facility, maybe where they're deployed and the department that they're deployed. But we also get a very large amount of client data in terms of their performance, their tenure, their engagement. These are all data that we track and we can use to build our models. So it's performance based. So we have the input data, and we have the label data, which is sort of the golden data. If you just had the input data, you're limited in what you can do. You can do clustering, you can do some sort of organization, but to really have predictive power, you have to have the output data, and that's a key component, and you have to have it at scale, and that's something that really helps strengthen our models. One of the typical machine learning techniques that we use, we have a lot of different dimensions. We use dimension reduction techniques to reduce the number of features that go into our models. Part of the models we use neural networks, part of our models we use random forest, and part of the models we use logistic regression. And really the thing that you want to take away is that if a model is simple and powerful and performs well, there's no need to make a more complex model where there's a risk of overtraining. So a great thing about logistic regression, it can be really powerful, and it can be if you have enough data, it can be fit very well. But if you have a neural network, you might have a risk of overfitting that, and that's something that we have to be really conscious of, especially if we're giving feedback on applicants. So when we train the model, we use the data that's available, of course, the input data and the output data. But the other part of machine learning is, what do you do with the output? And one of the challenges is that our customer is maybe not a data scientist. Our customer could be a C-level person or a hiring manager at a facility, and they might have no idea what area under the curve is. There's other issues where area curve for a prediction algorithm might not be appropriate because some of our employers that we have might have over 1,000 different job roles. And so do you create an area under the curve for each particular position, each particular match? And if you don't, how do you find the outliers? How do you identify the outliers? So even the typical data science metrics get a little confused. A lot of different roles, and you can perform sort of a stratified approach here. But what we really focus on is that we focus on the gap, the return on investment, and the impacts that come from there. So if we can identify applicants that stay longer, and there's a huge cost to hiring, that has an economic impact. So what we do is sort of translate our machine learning predictions to actually return on investment, and that's much easier for our clients and our employers to understand. But The one thing I really want to stress is that this is a prediction of a human event, and this is a really hard problem. It's much more difficult than image classification, much more difficult than a lot of high performance machine learning techniques. This is I would say it's similar to predicting a movement of a stock market, where if you have a little bit of information that helps you make an informed decision, it can have a huge impact, and that's what we see. Right. So I think the key thing to take away when it comes to bias in machine learning is how is it measured historically, and how are we going to change how this is measured? So historically, this is measured by disparate impact, and there's this rule called the 80% rule, and it's generalized maybe to the P rule, where you look at the positive rate of a particular category compared to the positive rate of the best performing category. And if it's at least 80% of the best performing category, then this prediction algorithm or this label satisfies the 80% rule. And that's sort of the current standard in order to measure disparate impact on a minority class, whether it's race, religion, or sex, or national origin. And we can do better than this. And this is where we're using machine learning techniques to certainly improve this. So I'll just put in sort of the scale of ways to measure bias mitigation in AI. And maybe the more naive approaches in their maybe early 2012 or so, the strategy is just maybe unawareness. Any type of input that might be correlated to a protected class, as described in the Equal Employment Opportunity Commission, you remove, and you don't input to the model. And that may be satisfactory, but what we found was that there's latent correlations that exist. The current status quo was, well, as long as you satisfy the 4/5 rule or the 80% rule, you've done a good job. And there's some statistical significance that needs to be satisfied as well. But 4/5 is still not, still can lead to a disparity and an increase of disparity. So we want to address this in a way that is actually takes advantage of the power of AI machine learning techniques that are relatively recent. So we call these techniques the adversarial fairness. And basically, we use an AI as a critic to try to identify bias in your predictions, and you use an adversarial network to make sure that you defeat the most powerful critic. So that's the outline, and we'll go into a little more detail on that implementation. So the idea is that we have generally we have our goal is to remove latent correlations that are related to protected data in the input model. And we create a GAN-like network, but the difference is that we have two prediction measures. We have one is how well does it do on the actual prediction in terms of success in the labor market and after they're hired. And the second one is how well can we fool the adversary. So the first cost function is atypical of GANs, and this is sort of a secondary requirement. The other thing is we have lots of the EEOC /performance data. Without that, you can't perform this task. So that's one of the things that makes this possible. And the metric that we use to determine how well our algorithm works is the AUC of the adversarial network. So this is something that now we can quantify. We can quantify at a much finer degree than the previous disparity rule and the 80% rule or the P rule. And from that, we can quantify how much latent correlations are left based on our classifier and based on our adversarial network as well. So some of our implementations that we've done using real data is that basically this adversarial network will take two probability distributions over the inputs that might relate to two different classes. So here on the right-hand side, we might have started off with unawareness. So we removed all the correlations that were we're there, and what we're left with is sort of a difference that you can see, maybe a little bit of difference. It might satisfy the 80% rule, but after doing our adversarial training, the two probability distributions of the majority class and minority class are indistinguishable, and that's great, and we can quantify this. So when we compare it to demographic parity in the P rule, we can see the impact. The impact is before our bias mitigation technique, we were within the good range, but we certainly made it more fair. And our strategy is, as we get more data, as we get more clients and more information, we can create stronger bias mitigation models. But we're already improving what was the status quo. And I think we're doing it using some of the more advanced machine learning techniques that are available. So the key takeaway, I think I'm right at time, but the key takeaway is that the metrics are hard. You have to choose the appropriate metric for our client. And the data sources, when you have some of these techniques that remove bias, you might open yourself up to more data sources in order to create the model. For example, commute time is one that might have some latent correlations to protected classes, but could be extremely useful in determining how long someone stays in a particular position. We can quantify our bias using the AC, and this is in production at Arena. We're really excited. It's been applied to more than 500,000 applicants this year, and this is something that latent correlation removal was considered really difficult and almost impossible prior, and now we're using some of the most advanced machine learning techniques to do the impossible. So we're really excited at Arena, and I think I'm at time. So I apologize. I didn't get any feedback from the.
Nope, you're doing good. Can you hear me, Patrick?
Oh, I never saw the video. So
there you go. Hi, Patrick.
I think if there are any questions, I don't know how much time I have. I think
Hi, Patrick.
A lot of time, but I'll wait for the.
Thank you so much, Patrick. What a fantastic presentation. At the current time, we don't have any questions, so they may come later. So what we're going to do is just wait a moment here. Again, Patrick, we really appreciate your time and what fantastic information you were able to share with all the attendees. So since we have no questions at this time, we're going to invite everyone, because we do have a break from 3:15 to 3:45. So we're going to invite on that break. It's a break that there's an opportunity to go into track 2 of the ML in sciences. There's a 3:15 to 3:45 break, as well as track 3 to ML in business. So again, we invite you to move over to the tracks from 3:15 to 3:45, ML in sciences and ML in businesses. You'll see the tracks. You have an opportunity to choose. We'll be back to the main stage with another fantastic speaker at 3:15.
3:45.
Excuse me, 3:45. Just to clarify, 3:15 to 3:45, we have 2 tracks that are running simultaneously. We will see everybody back here to the main stage at 3:45. Thank you again, Patrick. And if you can exit the stage, Patrick, if there's any questions, Patrick will answer them offline. And again, thank you, Patrick, for a fantastic presentation. You can exit the stage now.